So I should call everyone together. Okay, everybody, welcome back after lunch. Good to see everyone back. It's good to see everyone. These meetings, and you online too. It's great to have you here. So we're going to start with the session 2 of our AMOC science team meeting. And so this is the Observing System Implementation and Evaluation. And Kathy Donahue and I are co-chairing this session. And we'll start off with our invited talk, which is Nick Foukal from WHOI, who is going to give us a review of observing system implementation and evaluation.
All right. Is that good? Can people hear me? Okay. All right. That's loud. So, yeah, my name is Nick Foukal. I'm at the WHOI Oceanographic Institution, and I've been tasked with giving a overview or sort of retrospective look at the AMOC instrumentation, observing system implementation and evaluation. And this is a pretty broad topic. You can imagine that there's a lot of different dimensions to explore in this. And so for the purposes of this talk, I'm going to focus on reviewing sort of the past 20 years or so of the implementation strategy that has gone on and the literature that abounds from that strategy on these 6 different mooring arrays, pretty remarkable mooring AMOC monitoring system that we have. And then I will focus the rest of my talk on the evaluation component. And in particular, I'm interested in how we can facilitate evaluation in the AMOC monitoring system, and also how we can sort of adopt a common set of standards between the observing lines. And I guess one take-home message that came out pretty apparently in my research of this talk was that the implementation strategy, or the literature on the implementation side, is quite robust, but the literature on the evaluation side, with a few notable exceptions, is not all that robust. And so I think if you're interested in getting into this field, there's a lot of unanswered questions on the evaluation side, and I would encourage you to consider some of those forward. The other component that I wanted to say is this literature is quite large, and so I want a special thank you to all the people listed here who helped me navigate this literature. Okay, so on the implementation side, there are 6 different mooring arrays that I'm going to discuss, and I arranged them geographically here. I want to introduce them. I think we're all familiar to some degree with some of these. We've already been introduced to OSNAP and RAPID, for example. But I just want to go through them and make sure that we cover all of them. So from north to south, there's the OSNAP line in the subpolar North Atlantic. It's a multinational collaboration that is measuring the MOC, the meridional heat transport, and then the meridional freshwater transport at 30-day resolution from 2014 to present. I'm not going to go into the details of that because Susan's already covered that in her talk. The NOAA line is a German array. It's been implemented, or it's been in the waters in various configurations since 2006. It was originally a PIES array, and then since 2016, it actually has tall moorings on both the western boundary and the eastern boundary. So I'm classifying it as a trans-basin mooring and PIES array. It's at 47 north. It measures the MOC at bi-monthly timescales since 2016. RAPID array is also, you can see there, we've already heard quite a bit about it, but it measures that 10-day resolution from 2004 to present. And then the MOVE array at 16 north measures the western boundary, or the western basin, and measures the southward flow through the western basin via PIES array. It measures the MOC at daily resolution from 2000 to present. And then in the southern hemisphere, we have these 2 lines, TRACOS moorings, or trans-basin PIES array at 11 south, and then, the trans-basin PIES array at 11 south, and that measures the MOC at 5-day resolution from 2013 to present. And I would just like to say that that actually just was published for the first time in 2021. So if you're not familiar with the data from those are just recently available. I came across those during my research on this. And the Samba array at 35 South is another transbasin PIES array that measures the MOC and MHT. And I believe the meridional freshwater transport is also part of, or is going to be. That's a daily resolution from 2009 to 2010, and then from 2013 to present. And then I should also mention that there are various other monitoring lines that have been implemented across the Atlantic. There's Argo and sea surface height lines at 41 north, and then at 20 south, 25 south, 30 south, and 35 south. There's also commercial ships that have been instrumented, namely the Oleander, the Nuka Arctica, and then the Noronha. And then there's hydrography, and there are many different hydrographic lines and XPT lines that have been used to measure the AMOC, but notably OVID in the subtropical and the subpolar North Atlantic. I should also mention there are continuous measurements of the overflow waters in the Denmark Strait and the Iceland-Scotland Ridge that have helped us constrain the densest water mass. All right. So there's two other components to these arrays that I want to introduce that come up quite a bit in the evaluation component. We've already touched on the fact that the reference velocity is a very sensitive subject, or a very sensitive topic to the overturning calculations, and then also the coordinate system. And so with any of these endpoint geostrophic arrays, we can only calculate the velocity shear. And so, of course, we need to reference this to a reference velocity. And I should mention here that satellite altimetry is partially developed to do just this, although I will touch on a few reasons in a few slides as to why that is more difficult than you might imagine from a bird's eye perspective. So the result is that each one of these mooring arrays has developed a different way of referencing their velocity. And so here at OSNAP, they use the time mean altimetry plus the barotropic velocity that is chosen to zero the net mass transport. This is sometimes called the compensation transport. NOAA, could not find, there's no publications yet on the full transbasin mooring array. There's plenty of publications on their individual PIES arrays where they use altimetry to reference their velocities, but until we get a publication from on the transbasin mooring array, I'm not exactly sure what they're using for the reference. At Rapid, they use this compensation velocity to zero the net mass transport, and then at MOVE, they use a level of no motion. TRACOS, they use a time-varying barotropic velocity from PIES, plus a time mean level of no motion at around 1,100 meters. And this is because of the leveling issue between two PIES, that you don't necessarily know exactly where on the geopotential surfaces these PIES arrays are, and so for the time mean, you need a level or a independent measure of the reference velocity. At Samba, they also use this time-varying barotropic velocity from their PIES arrays. Then they use a time mean from ECHO too. This other component is the coordinate system in which the AMOC is reported in. And it's quite simple to explain, but basically in the northern two lines at OSNAP and NOAA, they are reporting their data in density space. And then at Rapid, MOVE, TRACOS, and Samba, they're using that space. So I want to, with that background in mind, move on to the evaluation component. And I guess there's a couple of different ways of going about this evaluation. And I guess, in order to organize my own thoughts, I came up with a set of two recommendations that I think would be very nice for all the monitoring lines to adopt. And so I think the first one is to adopt a common set of standards between the mooring arrays. And there's many different ways in which that can be implemented. One is to report that I'm going to make the argument that we should be reporting these overturnings in density space, and I'll elaborate on that in a second. And then also reference the velocity shear to satellite altimetry. I know that's difficult, but I think it should be done. And then publish the time series of the compensation transports. I'll explain that in a second too. The second set, or the second recommendation, is to conduct more OSSEs. And so these are observing system simulation experiments, and we've been talking about them during the discussion a little bit. But essentially, they are where we implement the observing array into a mooring, and we observe how much the observing array in the model compared to the model truth, and what that ratio looks like. And Susan actually brought this up earlier, that we should be using the entire AMOC observing system rather than individual arrays. I also want to acknowledge that we should be really looking at the meridional heat transport and freshwater transport in addition to the MOC when we do OSSEs. Most of the OSSE studies that have already been published only focus on the MOC, but they're similarly important to look at the meridional heat transport and freshwater transport. And then I think we need to be doing this across multiple models. And so that's the only way we can get to the point where we can actually essentially adjust what we are observing in the real world to compensate for these offsets, or we could be missing. Okay, so this first component, I think we should be reporting the overturning in density space, and I want to dig into that a little bit. And in order to do so, I'm going to go into the modeling world a little bit. And this is a comparison of the AMOC stream function in depth space on the left and density space on the right. This is from HICOM 112th degree model, covers from 30 south up to 75 north on the x-axis. And on the left, you can see in depth space, we are exaggerating the top 1 kilometer of the stream function, and then we're compressing the bottom 4 kilometers. In density space, the y-axis is also nonlinear, but we're actually doing the opposite. We're compressing the upper water column and expanding the lower water column. It's important to understand when you're comparing these two that a lot of times we don't compare apples to apples in terms of y-axes. And the point that I want to make here is that across all of the recent results in high-resolution models, the structure of the AMOC stream function in density space is very robust, in that we have a subtropical mode water cell, that's this light water cell here, and then a North Atlantic deep water cell, which is in the denser water classes down here. And so this cell gets completely or almost completely neglected when we look at it in depth space. So much has been made about, about the overturning circulation in density space in the subpolar North Atlantic, where we have horizontal water mass transformation across the subpolar North Atlantic. But I would also make the case that in the subtropical North Atlantic, and RAPID is shown in the blue vertical line at 26 north, it's also that the stream function at RAPID also looks very different in density space. The other component that has come out of these high-resolution models is that the stream function in density space gives us a lot more information about the actual three-dimensional velocity field. So, for example, you can see in the light water masses up here, this is a northward flow of very warm subtropical waters that forms subtropical mode water and then recirculates southwards. And so that is completely neglected in depth space. And also, we miss this maximum in overturning in the subpolar North Atlantic that's present in the density space, and it aligns with what we know in terms of water mass transformation in the subpolar North Atlantic. So when we compare that to density space or to depth space, we miss a lot of that information. So the other point is I want to make that the subtropical mode water cell is actually very important. And so when we look at the maximum AMOC in depth space at RAPID, for example, we are almost always, and I think always, isolating the North Atlantic deep water cell, which is down here. And we don't focus at all on the subtropical mode water cell. And so if you look at this in latitude space, or as a function of latitude, and compare it to the meridional heat transport that's shown here on the right, this bump in the meridional heat transport between 0 and 40 north aligns almost exactly to where this subtropical mode water cell is occurring. And so you can see in the background, there's about 0.6, 0.7 petawatts of meridional heat transport moving northwards, and then we get this big bump from the equator to 40 north. And that corresponds exactly to what is going on in the subtropical mode water cell up here. So this, oh, I guess I should say that before I get to the conclusions on here, I got kind of curious when I was looking at this as to the timescales of variability in these different cells and whether they co-vary. And so I had access to output from Viking at 1/20th degree. This is monthly output from 1958 to 2019. So we had 62 years of data. This is the mean stream function in density space. And what I did was I just outlined these two cells and looked at their time series. And so this is their time series, their transport is a function of time on the top right. And what you can see it's also present if you look at in frequency space, is that the North Atlantic deep water cell, this lower frequency cell, is stronger, and it also has lower frequency variability, or it has stronger multi-decadal variability. So at these periods of 31 and 62 years, you can see the North Atlantic deep water cell has higher spectral power. So that's all to say that these two cells do not operate in concert. They have different multi-decadal variability. And the subtropical mode water cell is neglected in depth space, but likely important to processes with structure in the upper ocean, such as meridional heat transport or biogeochemistry. The density space AMOC stream function contains more information on the water mass transformation than depth space stream function as well. And so we've all heard the common refrain that when we go into stream function space, we compress a three-dimensional flow into 2 dimensions, and we lose a lot of information in that process. My argument here is that we lose less of that information in density space, and so we can recover more of the water mass transformation. So my plea is, please report your overturning in density space. I realize that's not simple, especially at latitude or at rapid, for example, the way they currently operate or the way they currently report their data. However, I think that we can learn a lot from actually looking at the vertical structure. All right, the other component is to reference the velocity shear to satellite altimetry, and I've compiled this into sort of a highlights of satellite altimetry, and then I'll show you some lowlights in the second slide. So the first component is that altimetry provides a directly measured level of known motion to reference geostrophic shear. And so we can calculate the surface geostrophic velocities. We can reference the baroclinic structure to those and come up with a full depth velocity field. At rapid, this has been used to recover, basically, they compared an altimetry referenced upper mid-ocean transport. So this is the geostrophic transport across the subtropical North Atlantic. And it closely tracks the zero net mass referenced upper mid-ocean. And so that's shown in this Alejandro Sanchez-Frank's paper in 2021. So these are time series from 1993 to 2019. You can see the rapid data starts in 2004 here, whereas the altimetry goes back to 1993. And if you compare the red to the blue curves, that is the altimetry referenced versus the reference with the zero net mass. So they do a very good job of tracking one another. So that's really promising. If you also compare that, or I guess I should say the correlation there is 0.79. If you compare that, or if you add in the Gulf Stream and the Ekman components to get the full meridional overturning circulation, that correlation is even better at 0.87. So there is promise here at rapid. At NOAA, altimetry is well correlated to the shipboard and moored data, and they've shown this repeatedly from their surface velocities ships. And so altimetry does seem to be a good metric of the surface velocities at NOAA. And then the last part I'll say is that altimetry and Argo could sustain a cost-efficient AMOC monitoring array. So if we're able to validate altimetry as a reference velocity, could be very cost-effective going forward. now I promised you some lowlights. The referencing to altimetry is difficult because sea surface height contains both baroclinic and barotropic components. And what we're really after with the reference velocity is the barotropic component. And so there's this somewhat, I guess, noise in the data of the baroclinic component. At OSNAP, the time-varying altimetry is just too noisy compared to directly measured ADCPs. And it's been proposed or posited this could have to do with issues with the geoid in the subpolar North Atlantic. There's a lot of complex bathymetry. However, that wouldn't necessarily impact the time-varying altimetry. And so we really need to get at the heart of what is going on, why there's not these direct correlations between the ADCPs and the altimetry. I should note that altimetry has done a lot of comparisons to surface drifter data sets and made a lot of really good improvements on that front. But there aren't many trans-basin mooring arrays with ADCPs to compare to. So this could be a really good opportunity for altimetry, too, to compare to in situ. So I think we need to come up with a common answer as to why the altimetry is not working at OSNAP, and the time-varying component. Most OSCEs at RAPID have not tested sea surface height to reference velocities. And so there have been quite a few OSCEs at the RAPID line that I'll show you in a second. And they test the sensitivities to many different reference velocities, but for various reasons, they haven't tested to sea surface height. There's one example Pablo Sina's 2018 paper did, but I think when we do these OSCEs, altimetry should definitely be on the list of things that we are testing. The last component of this sort of adopting a common set of standards would be to publish the compensation transports. And so these are the barotropic, or sometimes called hypsometric velocities that are added into the velocity field in order to zero the net mass transport. And it's pretty difficult to find what these values are. And I noticed that Gokhan showed them earlier in the 2021 paper. They're also at RAPID. They were published in 2018 in Eleanor Frackel-Williams' paper. This is the dashed black line in this plot. But we really need to get an understanding and be more open about this. And so I propose that every time that a new data set is released about the transports, every 2 years, for example, at RAPID and OSNAP, they also publish the compensation transports next to them. Because it's not fully the uncertainty, but it does give us an idea of how close we can get to closing the mass budget just with what we're observing directly. So at RAPID, this is about 12 sphere jumps. There's quite a bit of variability that's shown here in this time series, especially in 2009, 2010. OSNAP, it's 0.7 sphere jumps, so it's relatively low, but there is relatively large time variability in the 3.3 sphere jumps. At Samba, it's 6.6 sphere jumps, but it's attributed to the Antarctic bottom water coming through, and it's time invariant. And at NOAC, it's somewhere between 5 to 10 sphere jumps, but I think we'll have a better idea of that once the publications are ready. Okay, so my other component is to conduct more OSCEs, or my other recommendations. And so I think we just need to be a little humble, I guess, in the sense that this relationship between what we observe and what the actual truth is not, this ratio is not going to be 1. And so what we can do is we can do this in a model, and I think I'm not going to go into the details of this because I think we've already discussed it to some degree, but we can deploy these instruments into the model and see what we get. You know, I'll just go over some highlights. Philly Lee did this in 2017 for the OSNAP array and got that in the ORCA model at quarter degree, the MOC was underestimated by about 1.5 sphere jumps, and the MHT was underestimated by 0.04 sphere jumps, so about a 10% offset. And so if we did this across multiple models and had more confidence in this, we could get to the point where maybe if it was 1.5 sphere jumps across all models, we could actually add 1.5 sphere jumps to our OSNAP array. That's a pipe dream, I will say, but I think that you know, we need to do more of these. In terms of the amount, the scale of these observing arrays, we need to do a little more on the evaluation side. And I'll just highlight a few. So Babu Sinha had a 2018 paper that did this at Rapid, also Gokhan's 2021 paper. But since I'm running out of time, I'll just go to this sort of synthesis of all Aussie studies. So this is broken down by array on the left. So this is different arrays, and then the methodology papers, the Aussies that focused on MOC, MHT, and meridional freshwater transport. And I'll just say that we are missing quite a bit of information here. So rapid MOC, we have, you know, a fair amount of studies on it. Outside of that, especially the meridional heat transport and freshwater transport, it's really lacking also in the total system. And so we described how doing this across multiple arrays would be very useful rather than just single arrays. It's also a little bit more fair to the models because we're evaluating the models across multiple latitudes rather than a single latitude. Okay, I'll leave these recommendations up, and I'll just say this last point, which is that we really need to capitalize on this incredible period of intense AMOC sampling. We should not take it for granted that this is going to continue into the future, and these evaluation studies, I would argue, should be done while these are in the water so that we can actually optimize them.
All right, so we'll take questions. I see one question from Chris Pykuch first.
Thanks, Jenny. And Nick, great talk. It was really informative. I'm going to take off my AMOC hat and put on my sea level hat. I love that you're talking about altimetry here. I didn't know that OSNAP uses time mean altimetry as a reference, and you're advocating for using the velocity shear. Last piece of information, you alluded to things being a little bit messy around OSNAP. For both the time mean and the time variability, are folks using altimetry accounting for gravitational attraction effects on sea level? Because they're pretty big around Greenland.
Right.
And that's not corrected for if you sort of download a VISO or CMEMS.
No, the answer, yeah. So the geoid is changing, right? I mean, because of Greenland melting. And it's actually, Chris, I believe you're a co-author, but I think Rui Ponta had a paper on this to look at the spatial structure of that. And I think it's really important. But that should not affect the, month-to-month reference velocities. That would affect sort of a linear trend. So I think first we need to figure out what's going on month-to-month and then maybe implement that on a linear trend level.
Yeah, so certainly Greenland would give you a seasonal signal and sort of this decelerating trend. But again, satellite altimetry seeing the whole Earth system. So if you have terrestrial water storage, other mass flux in the climate system that could give you interannual variability, you can, there are products that estimate this. People like Surendra Adhikari have published based on GRACE, these SSH maps month to month. So one could in principle very easily sort of adjust altimetry for these things and see how much of a difference it makes.
That's a good point. I was thinking more of the linear trend, but you're right. Thanks.
I see some comments online from Eleanor and Renellys towards Nick. Did any of you guys want to unmute and just summarize what you guys were discussing?
Sure. Nick, great talk. Yeah, it looks like Renellys and I are having a little chat in there again. I was just going to comment one more thing on rapid referencing velocity shear to altimetry, that scale factor is needed at 26 north as well. So if you use the raw altimetry, you get variability that's too large. So the correlations are great, but you can't necessarily just use it in a straightforward way.
Yeah, and I think what I was saying in the chat was that Marianne Kersale did comparisons with altimetry and the dynamic heights from the moorings and found good agreement in the interior, but not on the boundaries. So, and then there's this, as you mentioned, this whole issue of the barotropic versus the baroclinic geostrophic velocity contribution.
Yes, yeah, I agree. That's a good point, Eleanor, about the offset. I did not mention that, but yes, the variability seems to be there, but it was offset. And the boundaries are always an issue with sea surface height, right?
All right, so I think I see some eyes in here that hint that they want to also ask some questions, but we'll save it for the discussion after the session. We'll move on to our next speaker. So thank you, Nick.
So our next speaker is remote. That will be Ben Moat from the National Oceanography Center. And he will tell us about sustaining observations at 26 degrees north, a new design for the rapid array, and recent variability of the Atlantic meridional overturning circulation. So we're pulling you up here, your screen.
So can you hear me as well?
Yes, we hear you. Yep.
Brilliant. Good to go? It's full screen and
Good to go.
All good to go. Yep.
good to go. Thank you. Well, I would love to be there for these 3 days, but we'll have to still go remotely. So I think here we have a wonderful example of collaboration between the UK and the US, through Dennis and Molly, looking at the Florida Straits transport through the cable, and then with Bill Johns' group in Miami. So today I'm going to talk about RAPID at 26 North. So RAPID, as you well know, is between the Bahamas and the Canary Islands. What I'm going to talk about today is we updated the time series of the AMOC last year, and that was up to February 2020. So we're going to have a look at some of the variability in that new time series. And there's a link here, or Google it if you haven't got that data yet. And we've also been looking at, here I've said modifications, but perhaps optimization really of the array. So we have actually changed the design since 2020. And this is really looking towards more of, the questions are, can we get away from that dependence on the ships? Can we start to look towards using altimetry, using Argo to measure the AMOC or observe the AMOC, not just at 26 North, but perhaps through the whole North Atlantic. So has that moved on?
It looks frozen on our end.
Okay.
Video is working great. Okay, there we go. Good.
I've gone for too many. Bear with me. Right. Okay, sorry about that. So here's a time series that we released in released last year. So this is up to March 2020. So Gokhan said this earlier today. He showed this time series. So what you can see here, even looking at this by eye, you can see quite a high period up to about 2009, a decline through that. And then since then, even if you look at this by eye, really, I wouldn't say there's an overall decline through the whole period. So the main message here is that the latter period since 2009 is remained in a relatively low state. So we were on out at sea, an expedition in February, March this year to service the eastern boundary of the array. So we will produce the next update to the time series, and that will be in August this year, and that will go through to December 2020. Okay, it's moved. So if you look at, top left is the total AMOC, and in this case we've removed the AMOC, removed the Ekman. Ekman transport, Florida Straits current, the upper mid-ocean transport, the upper North Atlantic deep water, and the lower North Atlantic deep water. So if you look at the Florida Straits and the upper North Atlantic deep water, there's no long-term changes really to those two. If we concentrate on the upper mid-ocean, this is one that really contributes to that interannual variability of the upper limb. If we look to the lower North Atlantic deep water, again, this is the main contributor to the interannual variability. So let's look at the contributions to the AMOC. So the total AMOC at 26 North is a combination of the Florida Current, the Ekman Transport, and the mid-ocean. So here on the left, we have the monthly values of the stream function. On the right here in the grey shaded area, you can see the standard deviation of that variability around that mean stream function. So the larger the grey area, the more it's contributing to the variability. So from this, you can see that the mid-ocean transport is really contributing the most to the AMOC variability. If we break that down further, so the mid-ocean is a combination of the western boundary wedge, the west, mid-Atlantic ridge, and the east. You can see that the largest contributor is from this western region. So hence it's the most important part of the rapid array, really. It contains the most information. But importantly, for the next slides, you can see that the Mid-Atlantic ridge itself does not contribute very much at all to the variability. So it's not just about AMOC, it is about heat transport and freshwater transport. So this is work that Bill Johns has been doing. So here you can see that the total the total heat transport is about 1.2 petawatts, and most of that is in the overturning. So you're comparing the black line and the blue lines here, and you can see that most of the variability is in the overturning compared to the gyre. The relationship between the MOC and the heat transport, again, this is basically an update to Bill's paper, and you can see that there is a strong relationship between the two. We've got 96% of the variance really in the heat transport is explained by the MOC. So changes to the array. This is currently what the array looks like. We have basically an eastern boundary and a western boundary. During lockdown, December, January 2020, 2021, we removed the Mid-Atlantic ridge and we removed the Antarctic bottom water array. And then this year, February, March, we removed the deep moorings on the eastern boundary. Bear with me again, there we go. So what's the impact of removing these moorings from the AMOC calculation? So here, what's in these figures here is what portion of the array actually contributes to the AMOC calculation. Blue is we've replaced these with monthly climatology. So when we look at the difference between the two, you can see that the mean difference is virtually zero, and the standard deviation is 0.7 Sverdrups. It's very small. So again, removing those two deep moorings on the east, again, very, very slight change. Well, how far can we push this optimization? If we move further up the slope in the east, you can see that we actually remove the mean difference there is very large indeed, and it's quite unacceptable. What I will also mention is that Eleanor and Pete Brown got funding to put biogeochemical sensors on the eastern boundary. So we put these out in February, March this year, and they will be out for 24 months. As you can see, we've got, this is quite complicated, but if you pick the sensors up, you can see where we've positioned them through these moorings on the east. So we've got lab-on-a-chip sensors measuring pH, alkalinity, nutrients, oxygen, which we do across the full array anyway, pH and PCO2. So these will be analysed in 2 years' time. Okay, why are we doing this? Well, this is really to look at the upwelling systems around the Canary Islands, transfer of carbon into the deep ocean.
2 minutes.
Okay, well, final slide really. I just want to point out Eleanor has recently successfully got 8 million euros funding for this project, EPOC. And EPOC is really looking at the AMOC across the whole North-South Atlantic, across the whole Atlantic, looking at the natural anthropogenic drivers and also changes and impacts, so impacts for society. But what I want to concentrate on here is the observing system design as part of this. So Eleanor and the project are going to look at different ways to measure the AMOC, observe the AMOC across the whole Atlantic. You know, can we use Argo altimetry? Can we combine gliders, biogeochemical sensors? And we're going to put a drift-free bottom pressure sensor on the western boundary. We're going to put, and then use the stepping method to go up the slope as well. So I can stop there and just leave these conclusions up. So thank you.
Any questions for Ben? Yeah. Gökhan.
Hi, Ben. This is Gökhan. What are the cost savings associated with the reduction in or elimination of some of those spots?
So we have brought down the cost of the RAPID project by half by doing this.
That's quite substantial. So
yeah, and you know, before we did any of this, you've seen the analysis we did to work, you know, to look at whether it's, you know, it's feasible to do it.
Thank you.
Any other questions?
Thank you. This is Jake Ebbe from Moat. Sorry, I hear a big echo. But question for you, when it comes to optimizing the array, has the detectability of climate trends been taken into account? So for example, your standard deviations of the high frequency variability don't seem to matter much, but what about a small climate signal? Would you still be able to detect that?
So I interpret your question really as will we still be able to detect trends over long periods of time in it? And the honest answer to that is we don't know, but we have a plan using hydrographic data to actually look at this.
Thank you.
Any other questions? We have one more from the room.
Hi, Fred Casricio from NCAR. So you look at the mass transport contribution when you optimize the array, but you didn't say anything about like meridional heat transport, for example. So have you assessed that also?
Yeah, so we've looked at the heat and freshwater transports, and the impact again is very small.
Comment from Susan.
It's very quick, and it's really, to Jake's question, is a good one. And really, when we look to optimize these arrays, the question is for what? You know, and so what is the priority? If it is a long-term trend or decadal variability, is it MHT, MFT? I mean, at the rapid array, it's nice because so much of the variance of MFT and MHT can be explained by the AMOC, but that's not true at OSNAP. So the other thing is when you do change an observing system, we always worry, right? When we look at historical data, we always worry how much of a change is due to the shift in the observing system itself. So there are, I appreciate what Nick was saying, and I agree that we need to work toward this standardization, but there are some concerns when you start changing the method of observation.
Yeah, I don't like to change anything really, but to keep, I don't like to talk in terms of cost or money really, but we still have to find funding for these arrays to observe the AMOC. So we have to start to look at alternatives to measure it in terms of, you know, altimetry. What else is out there that we can reduce not just the cost, but the carbon imprint, you know, the ships, or the reliance on the ships and the big infrastructure. Can we get away from that in terms of a net zero oceanography?
Okay, so we'll move on to our next speaker, who is also remote. That will be Renellys Perez from NOAA, AOML. And Renellys, I guess you can share your screen with us. And Renellys will be telling us about recent observational advances from the South Atlantic Meridional Overturning Circulation Basin-Wide Array, or SAMBA, at 34.5 degrees south. And we see you, and we see your slides.
Okay, great. And does it advance?
It does, yep.
Fantastic. Okay, hello everybody. My name is Renellys Perez, and I'll be telling you about SAMBA. And I just want to say thank you to my co-authors who are listed above, and you can see from the affiliations, we're quite international. I would be remiss if I didn't say a few words about the larger SAMOC program that SAMBA sits within. The SAMOC initiative began in 2007 with the goal of measuring the strength and variability of AMOC-related transports in the South Atlantic, as well as interocean exchanges. And some of the countries that are involved in SAMOC are listed on the slide. There is, as part of SAMOC, there's the SAMBA array along 34.5 south. There's Guillomar's Tracos array, which consists of a mixture of tall moorings and bottom pressure recorders that was deployed in 2013. Okay, hopefully the animation works. And you see the Saga line, which was just deployed by Spain and Mexico in 2021. And then, as other people have mentioned, there are XBT transects that are measuring AMOC-related transports at multiple latitudes in the South Atlantic, as well as a lot of CTD transects and in situ and altimetry synthesis products in the subtropical South Atlantic. I didn't include all the lines, but they're in that subtropical South Atlantic region. There's also sustained CTD and XBT lines in Drake Passage and south of South Africa. Some of the reasons why the South Atlantic is so special: it's the only basin for which we have equatorward heat transport. It's a gateway for waters formed in all of the other ocean regions to exchange, to mix, to form, and ultimately reach the North Atlantic. There are idealized and theoretical model studies that suggest AMOC can be either monostable, and in that case, it would be slowly varying, or bistable. And if it is bistable, there's an on state and an off state with adverse implications for society if there's an off state. Most of the few observations we have of freshwater transport in the South Atlantic suggest that the freshwater transport is negative and we're in a bistable regime. So how has SAMBA grown over the years? SAMBA began in 2008-2009 with 4 NOAA pressure-equipped inverted echo sounders on the west and 2 French CPIs on the east. A PIs measures the vertical acoustic travel time, from which we infer dynamic height, and then we estimate the baroclinic component of geostrophic velocity. They also measure bottom pressure, so this is particularly important to the discussion we were having earlier. From that, we can get the time-varying barotropic geostrophic velocity. And whenever there's a CPIs, that has a current meter, so that also provides a bottom velocity measurement. SAMBA has grown over the years. In 2012, Brazil added more CPIs instruments on the west. South Africa added, and you can see the green symbols, tall moorings on the east, and France added more CPIs on the east. Since then, Brazil in 2019 added some interior moorings on the west of the Mid-Atlantic Ridge. And in early 2021, Spain and Mexico deployed Saga, which involves tall moorings and PIs nominally along 9 West. And the southernmost PIs was loaned to them from the SAMBA East team, and that provides another data point in the ocean interior on the east side of the Mid-Atlantic Ridge. It links Saga and SAMBA. So if you look back to this map, it's that pink one right there, that pink symbol. In later 2022, we plan to deploy tall moorings on the western boundary. That is part of the I-Atlantic and Tri-Atlas projects. That those deployments have been delayed because of the pandemic, as have a lot of the cruises on the western boundary. Those projects involve collaborations between Argentina and the European Union. And the tall moorings will be providing direct measurements of the Brazil current, deep western boundary current, as well as changes in water mass properties. So a quick flyby of some of the results we've gotten from Samba. There's a multi-year daily time series of the MOC volume transport that was generated by Meinen et al. In 2018, and that uses the most onshore pies mooring sites A and Z. So it's just 2 sites. And what we learned from that data is there's high variability from very short timescales up to interannual timescales. The standard deviation of the volume transport is 8.3 sverdrups, and the mean northward transport is 14.7 sverdrups. In this analysis, it was broken up the time series into the contributions from the density-driven changes, or the relative term, which is the blue line, the pressure-driven term, which is the green line, that's the reference contribution, and then the Ekman contribution, the wind-driven component. And what you can see here is all of those fluctuations are important, and they're all contributing to the total MOC, which is the top line. I won't go into it, but if you want to look at the paper, you can. We found that both boundaries were contributing to those pressure and buoyancy-driven changes pretty equally when you consider all timescales. In that study, we also looked at the seasonal cycle and found that the MOC seasonal cycle appears to be semi-annual at this location, with a 4 sverdrup plus or minus range and peaks in austral winter and summer. And when you think about those 3 terms, density, pressure, Ekman, they were all 3 important for the seasonal cycle. And one thing that I'll just point out is that the reference, the pressure-driven component, is out of phase with the other components, and those are all independently measured quantities. So that's kind of an interesting result from the study. We also found that density and pressure changes on the eastern boundary turned out to be most important for the seasonal cycle, more so than the western boundary. In a subsequent study, Marian Kersale took the better instrumented part of the record from 2013 to 2017 and used that to generate a more nuanced estimate of the MOC. So going from 2 sites that only resolved the flow down to the 1,300 meter isobath, but including more sites that resolve the deeper flows. And specifically, we can estimate at the same time the upper cell transports and the lower cell abyssal cell transports. Marian found a mean upper cell transport of 17.3 sverdrups, which was stronger than the previous mean estimate because she did not include that first 2 years from the pilot data for which the MOC was weaker. And then the lower cell has a transport of 7.8 sverdrups southward. And just to provide a little bit of nuance here, we don't apply a zero net mass transport assumption. We just use a model to provide a reference mean. Okay, so with more instruments, the estimated MOC that Marian found was far more energetic than the previous study, and that's due in part to mesoscale and eddy variability at this latitude. And the standard deviation nearly doubled compared to the 9-site calculation. The abyssal cell was also very energetic. You see the time series of the abyssal cell transport in the lower plot. And from what we can see from this 4-year record, the variations in the abyssal cell and the cell above are largely independent of one another. I think they had a correlation of 0.4. So there's no meaningful correlation on this timescale. There might be on longer timescales. There was no meaningful volume transport trend yet detected based in the abyssal cell or in the upper cell during this 4 years. So we need longer time series to study interannual variability, as well as do sensitivity studies like what Ben was mentioning, where we want to see how inclusion or removal of certain stations impacts the MOC estimates. These observations were also used to estimate the heat transport time series for the same time period using hydrographic and altimetric data in the interior between the most offshore moorings. What we found was that the heat transport has a mean of 0.5 petawatts and significant variability. The standard deviation was about 0.8 petawatts. We also found that not only was the heat transport strongly correlated with the MOC, like was mentioned before, that other studies have found, but it was also modestly anti-correlated with the abyssal cell volume transports. So that was a new result. And in this case, for heat transport, the baroclinic component, the relative contribution, the density-driven changes are what's dominating the heat transport. But the Ekman component and the bottom pressure reference component is still important. Okay, so I don't have lots of time, but I can say that we can compare estimates from different platforms. So here I'm comparing the heat transport time series from the moorings with the XBT estimates. And what you see is there's a lot of fidelity in the mean estimates, but The XBT transects take 1 or 2 weeks to cross the basin, and what the moorings are telling us is that the time series is quite variable on high frequency timescales, and that can bring up basin opticity issues for transbasin sections. On the other hand, we have the XBT results for much longer than we have mooring results, so they provide excellent long-term context for what the moorings are telling us. In addition to moorings and hydrographic transects, we also have synthetic products that merge altimetry and hydrography to generate 30-year time series of heat transport, volume transport at multiple latitudes in the South Atlantic. And so what we can do at 35 South is compare all of those methods. And as I was alluding to earlier, there's still not a lot of agreement between the various techniques, given the timescales of overlap that we have for the data. And some of the differences might stem from different time and space scales resolved or the observational methodologies, but there might be physical reasons for the difference. For example, as we've been talking about, how do we measure that barotropic contribution? And so we need longer records to understand and reconcile these differences. In 2017, there was an international transbasin section along 35 South. And what I'll just briefly say is Manta et al. Estimated the heat transport as 0.27 petawatts because he found that there was a presence of a lot of cold core eddies that lowered the heat transport. They also found during this cruise positive freshwater transport. And that goes counter to the other observations that we've had before that were negative. So this one observation suggests that AMOC is monostable. So we obviously need much more freshwater transport estimates, and we need a time series of freshwater transport to sort of understand how variable it is and what the mean is and what the standard deviation is of these freshwater transports, and whether we're in a monostable or bistable regime. Thank you. As longer data records become more available, we're going to start seeing more model data comparisons in the South Atlantic, and it's important as these models are used, these models predict a 40% reduction in the strength of the MOC, as found recently in a study by Wilbur. And so we're working with model groups such as Fred and Gökhan at NCAR and Jonathan Baker and Laura Jackson at the UK Met Office to compare SAMOC and SAMBA estimates with those models. Just like other arrays, and I won't go into all of this, we're measuring a lot of things on the boundaries. We're using our observations to estimate the variability of the Brazil current, deep western boundary current, abyssal flows, detect long-term warming trends in the deep abyssal ocean, and on the east, the resolved eastern boundary currents like the Benguela current and the deep eastern boundary current. So I'm going to conclude and say that the SAMOC-SAMBA observational committee has made exciting progress. We've got a lot of observations and we're learning just how variable the MOC is. The larger science community is starting to use those observations to study mechanisms controlling AMOC and boundary current variability. We want our observations to inform improvements to models, and as longer records become available, we hope that will happen more and more, and that the public will use these products. And the longer data sets that we have, we can do more of these multi-site comparisons, such as the one that Eleanor Fracchia-Williams did, and Dennis Volkov has been doing on the every year in the State of the Climate reports. I'll just briefly say that we're working on a SAMOC observational science review article that should be submitted next month. And we're also working on a short article that goes over SAMOC's history, especially its history of diversity, inclusion, and international collaboration. And we're actively working on updating the time series through the middle of 2019. We haven't had cruises on the West during the pandemic, and so we're hoping to have 2 cruises in 2022 and update the records further. My last slide, I just want to thank all of our funding agencies and partners without whom we couldn't do the SAMBA work, and to the larger community for their support of our efforts. And a lot of work goes into going into the field, maintaining these arrays, collecting, processing the data. So we thank all of the people that routinely do so. And I just want to thank the US AMOC science team for bringing us all together over the past decade and a half. And with that, I'll stop. Thank you.
We have time for one question. Is there anyone in the room or online that has a question for Renellys? All right, I don't see any hands, so we'll move on to our next speaker. Thank you, Renellys.
Thanks, everybody.
Okay, so our next speaker is in person, and it is Franz Philipp Tuchen from NOAA AOML, and he will be telling us about transports and pathways of the tropical AMOC return flow from Argo data and shipboard velocity measurements.
Hey, is this working? Okay, yeah, thank you. So yeah, my name is Tuchen. I'm just started a postdoc at NOAA AOML, so that's on my badge actually. But the research I'm presenting, that's work I've done with Peter Brandt, Joke Lübbecke, and Rebecca Hummels back at GEOMA. It's going to be tropical, and it's going to be more on the upper ocean, so the return flow, transports and pathways associated with it. So I just want to use this overview slide to show you the situation in the tropical Atlantic. So as you can see in the tropical Atlantic, both AMOC branches, the upper and the lower limb, they are pretty much concentrated to the western boundary. And we are especially interested in the western boundary circulation at 11 south. So you've seen the Fracas line at 11 south, where we have a western boundary moving array, and especially the western boundary circulation at 11 south and in general in the tropics. It's actually consisting of 3 different components. We have the thermohaline circulation contribution, and then we have the wind-driven circulation or the wind-driven contribution, which further consists of the subtropical cells and compensating transport for the interior sphere balance. So we were especially interested in the superposition of these two components, the thermohaline circulation and the subtropical cells. So just as a brief summary, in a schematic view or in a 2-dimensionally only average view of the tropical Atlantic, we can think of the subtropical cell circulation as being forced by the easterly trade winds at the surface, which then are forcing forward Ekman transports in both sides of the equator. These waters are then subducted in the subtropics. Right, so they are subducted, or there's subduction in the subtropical gyres in the subtropics to thermocline level, and then at thermocline level, these water masses are brought back to the equator or to the tropics by geostrophic transport. And then the cells are eventually closed by equatorial and also by eastern boundary upwelling. And I always like to point out that there's, of course, also a geostrophic transport in the surface layer, which is at least partly reducing the overall Ekman divergence there. That's the subtropical cell circulation. Then on top, we have the thermohaline circulation component, which looks schematically like this. So in general, the thermohaline circulation enters so in general, the thermohaline circulation enters the tropics as a more or less subsurface intensified transport, but then leaves it as a surface intensified flow or surface intensified transport. And this already shows you how the thermohaline circulation also interacts and is a reason for the asymmetry of the two cells between the northern and the southern subtropical cell. So you can see also there's some water mass transformation or upwelling going on, which just is the reason for these upwelling arrows that are indicated here. And there's only one real, or there's most famously the paper by Rhode in 1983, who showed that about 6 rare drops of water is entering the thermocline layer, or what they called layer 2 water. And this value is quite important when we are estimating these subtropical cells, because the subtropical cells are mostly estimated at outside of the equator at about 10 north and 10 south, just deriving the horizontal transport. But then, of course, we are missing what's happening in between. So we always rely on estimates of the upwelling into the thermocline layer in between these estimates, or in between these latitudes of estimates. So that was one goal of this study, to revisit this transport, so especially this arrow, in fact, using the Argo data set mostly. So what we've done, we used the high resolution Argo mean field, so really just the mean field that comes at a 1/6 of a degree resolution. I also did a whole PhD actually on Argo data that was mostly on a 1 degree grid. So we're really interested to see how this new field or the high resolution changes the results. So I'm going to be comparing also both products in the next few slides. Then what we first did, we wanted to compare and to validate this new product, this high resolution product, to a well-known and a well-known reference at 11 South, where we have a mooring array and also repeated ship sections. So in total, we have, we did 12 sections in the last 20 years, which is showing here the mean, and then just indicating the two branches or the two main branches of the upper limb, which is the North Brazil undercurrent, and the lower limb, the deep western boundary current. Then we defined our AMOC return flow layer as or based on water mass characteristics. So using all these 4 water masses in the end. So just assuming that the interface between intermediate water and deep water also separates the upper and the lower limb, which is also indicated here by this 27.7 isopycnol. Okay, so then we first compared the meridional transport or the vertical structure of the meridional transport from the high resolution product with the ship section mean. So the ship section mean is shown here as a function of density in the yellow line. And it indeed agrees quite well with this light red line, which is indicating the meridional transport by the high resolution Argo data. So that was quite nice to see, and you can also see how the previously used 1 degree product underestimates the transport basically at all depths. We also did the same at 10 north at the western boundary, but of course we don't have, or we do not have a comparable reference data set there, so it's a bit hard to say harder to validate at least. We still see an improvement or an increase of transport when using the high resolution data set. And then on more or less on a side note, we also compared the data in the interior basins away from the western boundary, eastern boundary, just to show that in the interior it doesn't really matter if you're using the 1 degree or the 1/6 of a degree product. So it's it makes it also more possible for deriving time series in the interior properly. So yeah, just on a side note. We then calculated the western boundary transports for the individual layers, so just to give them some numbers. And we're also including now the Ekman transport derived from satellite wind stress data, at least for the surface layer. And as you can see again, basically South Atlantic waters, it enters at 11 south at the western boundary, the tropics at all layers. And we overall find, also now showing you in numbers, we're finding a good agreement between the high resolution product shown here in the gray bars and in the ship section mean, so roughly about 21 to 22 sphere drops of western boundary transport at 11 south. It's a bit different when we are looking at the 10 north western boundary transports. So in total, there's less transport. So it really indicates there must be also some other pathways away from the western boundary, which is known, but now also shown here in the Argo data, and also striking the absence of thermocline and central water, partly also due to the reflection of water, so these water masses are mainly not reaching the western boundary at 10 north, but are mostly reflected before reaching it. So that's going to be also the topic of the next, or at a later slide, definitely. So then coming back to the main goal of the initial goal, at least, of the study, we want to derive the transport into the thermocline layer, right? So what we did, we constructed a closed basin, so deriving meridional transports at 11 south and at 10 north over the whole basin, each individual layer. And then we assume that we are conserving volume at each layer or within each layer, and therefore we can start calculating volume balances. So for example, for the surface layer and for the high resolution Argo data in gray, we're just summing up the geostrophic component and the Ekman component. We get something like 11.8 sphere drops of transport divergence. Then we've added a freshwater input that is just taken from the literature of about 0.3 sphere drops, which then means that we are still missing 11.5 sphere drops. So this must come from below as upwelling. And this we did basically for every layer, just going through these layers. The number that we were looking for in the beginning was this 1.9, so it's about 2 sphere drops now, which is about only 1/3 of the REMIC value. That's quite a difference. And also interestingly, when we are repeating the study with the low resolution product, we do end up at a similar value as REMIC. So again, just indicating that the role of the resolution could really have an influence on the amount or on the estimate of upwelling. That was one of the main outcomes of this study. We then, because we saw that the ARGO data and the western boundary SIP section data agree so well, we expanded a bit our analysis, and I don't have time to go through the individual water mass layers, but we came up with schematics for the 4 different water mass layers that are defining our return flow layer, also by using further ship sections at 5 south, and especially the cross-equatorial sections at 35 west and at 23 west. It really helped us to get a feeling for this huge zonal mass, or this huge zonal exchange of mass in the tropics. So I cannot show these slides because they're quite complicated, I think, but I definitely recommend to look at them up in the paper. So I just want to spend the last slide on the summary of our return flow layer transport. Just showing you here the averaged meridional geostrophic velocities in the colors, and then adding the transport values that we are deriving by using these geostrophic transports in combination with the Egmont transport components. So in total, we end up with quite consistent values of between 16 to 17 sphere drops at both latitudes, at 11 south and at 10 north. And we also find that especially in the south hemisphere, the water masses or the return flow is very much concentrated to the western boundary. But then at 10 north, when it leaves the tropics, the mix between western boundary contribution and CLIVAR. 2 minutes? Or is it? Oh, 1 minute, okay. Okay, so then just going to the key points. Just summarizing what we've done. So we found a way we used this high resolution ARGO product and found a way to reproduce the observed transport from observations or from ship sections in the end, which is the thing that other ARGO products have struggled with, so especially at the western boundary. That was always the problem. And then we showed that this diapicking transport into the thermocline layer is probably less than previously estimated from lower resolution data. Then in the end, we combined our shipboard measurements with ARGO data and satellite wind stress data, and just came up with a schematic with a more or less comprehensive view on pathways and transport estimates of the return flow layer. Yep, so that's all. So thank you for your attention.
All right, so let's take some questions. One from Mike Spall.
So have you thought about potential vorticity budget? Water coming in 11 south has negative potential vorticity. Going out at 10, it's got positive. There's got to be a lot of mixing in between. Have you thought about how that transformation takes place?
No, we haven't done anything in this direction, no. But yeah, it's a good point, yeah. That's also another way to look at this, but no.
Question from Gokon.
I was wondering about the time scale. Maybe I missed it at the beginning. Time scale that you're considering. Is it the annual mean data that you're analyzing, or is it the seasonal monthly data? Because in that case, there's quite a bit of seasonality of the subtropical cells. They can penetrate all the way down to the ocean bottom with large transport estimates. But when you average them in time, like annual time scales, they cancel each other, and then you get smaller transport. That 2 sphere drops dipycnal mixing that you were mentioning, that's based on annual mean data?
So the ARGO data is really just a whole ARGO era mean, actually. That's like.
So it's the full average of that?
Yeah, so it's
okay.
2004 to 2018 complete mean. So it's the only way they really can provide. So it's the Römmick and Gilson climatology. So it's the only way, I guess, they are able to provide a product on this high resolution.
Okay.
There's no temporal variability at all.
Thank you.
But yeah.
Is it on? Yeah. Okay. This is Yao from Georgia Tech. So I have a question, and I'm actually thinking about your talk with Nick's talk, because in Nick's presentation, he showed several slides about the subtropical Moat water cell. first of all, I'm wondering if that cell is the same cell of your subtropical cell in the north. And the second question is, because in his talk, he has highlighted the Moat water cell in the north and further to the north comparing to 10-degree north, right? So I'm thinking that if you move your section at 10-degree north further north, like take 15-degree north, would you see a larger transport there? Because you showed that in the northern part, the subtropical cell is asymmetric due to the AMOC, right? Thank you.
Yeah, so I must say I also don't know the term subtropical Moat water cell, or at least I have not heard of it. But I think it's something different. So the SDCs are mostly estimated at 10 north and 10 south, because you have on the equator side you have another shallow overturning circulation, which are the tropical cells. So you don't want to you want to separate the subtropical cells and the tropical cells. And then on the other side, so poleward, you get the bifurcation of the equator, or most equatorial parts of the subtropical gyres. So the NEC and the SEC, which are bifurcating at about like 15 north or 15 south. So these are not really participating then in this overturning, which is associated with the subtropical cells. So you have to stay somewhere in between, like 5 to 15 degrees. So that's why they're always choosing the north and south, I would say. But yeah, so because of the motivation, I think, of the study, that we are really interested in the SDCs, we didn't move these latitudes to any other latitudes. So we stick to the 10 north and south latitudes. But yeah, I was also curious about the subtropical Moat water cell. Talk.
All right, I think that'll wrap up our Q&A for Philip's talk. So thank you so much again for your presentation. So at this time, we're going to head into a 1.5-hour break for the virtual participants and another poster session for the in-person. We have the physical posters from today up in the hallway. For the in-person folks, I do want to do a group picture. So if you want to gather out in the front of the building and we can take a group picture before we officially go into the poster session, that would be great.
I have the shuttle, so I'm going to offer to drive people one time, and I was thinking like 7:30, but maybe I should make some kind of announcement at the end.
I think.
All right.
It's good food, so.
Yeah.
Some people were struggling, right?
Yeah, there's been an issue with the clicking on the mouse, so just avoid the mouse, and if you just click on the keyboard, just
So, previous slide, next slide?
Yep.
That's all?
That's all.
Okay.
Yep. Anybody complaining about audio issues anymore? That was the last speech we do. It's kind of like nervous stuff. It's pretty nice. But other than that, yeah, I think this is working a lot better. Somebody, I don't know if anyone can try it. I'm sure they'll help Mike. Yeah, the tall people, it's just, I think it's just a little far. But I got you. Yeah, no. Transmission's harder, which is oh, they're already like connected, right? Yeah, so they flip them in. Back and forth. Then after that, turn green and. Okay. Wow, that's really. Not what I would say. What was available. My understanding. Yeah, so we'll still need to, if you're only using one Bigelow conference room. I don't. Maybe I don't know. Well, we'll need to confirm on that. Yeah. Oh, well, you better get up there.
So the AOML was already introduced this morning, so I hope you remember some of that. And this is a talk on mooring data in AOML, and Isabella Lebar and Leah Trafford McRaven helped out with the data, so they're co-authors. And then some of my PhD students at NIOZ as well. Get to the next slide. Yes. So as Susan and others explained this morning, the Imringer Sea east of Greenland, located at Oceanography East, is very important for the overturning, and there's deep convectioning happening there, but probably contribute to the overturning as well, although we don't really know exactly how yet. And some of the outstanding questions related to the deep convection are the interannual to decadal variability of convection and how that will link to overturning. The link to the hydrographic property changes that change the density structure, and then the importance of temperature versus salinity in the stratification, because in the future, stratification will strengthen both to warming of the sea surface and or freshening from the Arctic and Greenland. And the importance of fresh anomaly is included here as well for that reason. I just need to keep turning this way to hit the microphone. So this is from two profiling moorings in the Imringer Sea. One is the local mooring, the long-term ocean circulation observations mooring that was located there from 2003 until 2018. I'm just going to do it like this. That was located a little bit to the south, and you see a schematic on the left. So it had a profiling CTD that recorded profiles at a high resolution at daily intervals. Then the WHOI is a similar mooring that was placed there in 2014, slightly to the north. And then these records have some gaps in them, and they also don't record the surface properties. So I'm supplementing this with Argo data from this region around the moorings. And this ellipse is aligned with sea surface height contours and is avoiding the boundary currents and focusing on this low certification region. So these are the three records. On the top, you see a local mooring that had a pretty decent data return in the beginning. And then we had some problems with cruises that couldn't pick it up and problems with the profiler. Then the WHOI mooring has a very good record starting in 2014. And Argo is more intermittent, but fills up some of these gaps. So we've merged these time series. We checked for the consistency between the moorings and the Argo data. And then we made a time series with a 1 week running mean to smooth out some of the high variability. And some other data you'll see in this talk is from hydrographic sections, from bottle data from the early 90s, and CTD data from later, and from the ERA 5 atmospheric reanalysis. So this is what the merged time series looks like from 2003 up to 2020. And you see nicely the seasonal cycle in the upper layers and also some interannual variability. So you see temperature at the top, salinity, potential density. Then here you see the potential vorticity, and that really shows the interannual variability of convection. So when you have deep convection, you see these plumes of low potential vorticity going down in the water column. So through these records, we had a period where we started with a cold situation in the 1990s, and we had very weak convection, and over time, everything warmed and became more saline. And then convection came back, and that cooled and freshened everything. And especially at the strong winter of 2014-15, got very strong convection, very cold winter. And that returned us to a cold and fresh situation again. At the end of the record, you also see this surface anomaly, this stress anomaly that people are talking about, some posters about that appeared as well. And we're wondering how this influenced convection. Now we want to put this mooring in the long-term context also. So here you see the hydrographic record over the time period from 1960s up to 2020. And the mooring period is at the end here, and you kind of see a very smooth version of what is happening in the mooring record. So this is a time series that was published before in 2012, and I've recently added the last 10 years of that time series. And you can see the decadal variability in the Emerald Sea very nicely. Mostly you see the very fresh and cold periods first in the 80s, and then much deeper in the 1990s. You see this warming and salinification in the early 2000s, and then you see this return to cold and fresh conditions again. Now these are based on summer sections only, so they're not a direct measure of winter convection, but by comparing the hydrography from this last period to the mooring data, we can really see that this captures the interannual variability very well. Yes, sorry. So we're interested in the role of surface forcing versus stratification. And I've tried to capture all of this first in this graph, where we see here again potential vorticity that shows when there was convection. And in the top, you see both the buoyancy from the water column, as the black points are from the observations, And then I filled in some gaps with the red line, which is a seasonal climatology upon a long-term filtered intervernal variability. And then in blue, you see the heat loss from the atmosphere accumulating over winter. So it starts at the end of summer when you have maximum acidification, and then all the heat loss that is removed to the water column through winter. And what you already see is when this blue line dips far below the red line, when all the buoyancy in the water column is removed, you have this deep convection, especially true for this strong winter here. So we want to look a little bit more in detail what the role of temperature and salinity is in this stratification. So a very crude way to do this is to look at a density record, both a total density record and then two faked density records, one when you hold the mean temperature profile stable, and one when you hold the salinity profile stable, and you let the other variable vary through time. It's quite crude because in winter that means you might get unstable density profiles, but it doesn't matter in summer when you get the maximum acidification, and that's what we're interested in. So you see in black the total variability of acidification. In the upper layer, it's very driven by temperature. That determines nearly the total variability in black. You see a small contribution from salinity, and it is stronger in a couple of years when we had low surface salinity, for example, in 2010 and 2019. Now, if you go deeper, it gets a bit more messy, and you do see more influence of salinity. And especially in the layer up to 500 meters, at the end of the record, you see the salinity stratification getting higher. Now you want to combine this also with the surface forcing. So below you see the same plots as before. And you see higher stratification at the end of the record due to the salinity anomaly. But if you look at the cumulative winter forcing in the top plots, you see in the blue arrows are strong convection years and the red arrow is a weak convection year. You see also that the winter of 2019 was extremely weak. And that is the main reason why convection stopped in that year. Even if we would have a normal stratification, convection would not have happened in that winter. What you also see is that in the upper layer, when you have a fresh anomaly, all the heat in summer is maintained in the surface layer, and you also have higher temperature. So that does increase the stratification somewhat. So we want to see how this varies in a decadal record as well. So you can calculate the buoyancy content of various layers over the decades as well. And then you can put this now recent period into perspective of the longer record. And you can see that we're actually at a very low stratification now and at much higher about 10 years ago. Thanks. So we do the same exercise for the hydrographic record. We want to see what the influence of the temperature variability is on the stratification and the influence of the salinity variability on the stratification. And you see more or less the same picture again, although this time not in the seasonal sizable because we don't have it, but in the long-term record. And you see that the influence of salinity is fairly low, quite stable, or not low, but at least stable. And the influence of temperature is much higher. Only when you go to the deeper layers, then the salinity becomes as important as the temperature variability. We would like to know how this relates to the surface fluxes also on these time scales. So these are the cumulative surface forcing from era 5 again over this time period, and then filtered with a 5-year mean to smooth it out a bit. And negative fluxes is when the ocean is losing heat. And you see that these periods of strong heat loss also coincide with periods of strong buoyancy loss. And this last period of very low stratification, or the strong decline from 2010 till 2020, is really forced by strong surface heat loss. And you see a very low variability in the freshwater forcing again. Now, this is, of course, not all the freshwater forcing. This is only evaporation and precipitation. It's not freshwater from Greenland. It's also not advection. So that could add to that. So to summarize, we have a very nice record from the Immingham Sea now. We see intermittent convection with an increase since 2007, and then a strong transition after 2014. We see that the subpolar fresh anomaly has added to the freshening, not just at the surface, but also in the water column. And so far, we mainly see the internal variability in the surface forcing. So temperature is important in the upper layers, salinity more in the deeper layers. This might change also when we're adding much larger quantities of fresh water in the future, which we haven't tested yet. And then this stop of convection recently seems to be mainly a result of a very weak winter forcing. And I want to.
So I think we have time for one question. I'll take. Wilbert, go ahead.
Thanks. Very interesting, Femke. Thank you. I was wondering, do you have any sense of how much of that interannual variability in the surface forcing is kind of related to synoptic variability in the atmosphere, like Arctic cyclones and things like that?
Yeah, it's mostly related to Greenland tip jets, forcing this very specific heat loss near the southern tip of Greenland, and that's related to the NIO. So when you have a high NIO, you have lots of tip jets as well.
Great, thank you.
All right, should we move on to our next speaker? Thank you.
Okay, so the last talk of this session is Tom Rossby from URI, and Tom will tell us, answer the question, what can hydrography between New York and Bermuda tell us about the strength of the AMOC over the last
Just hold this.
This is a bit of a mea culpa because I've somewhat stuck my neck out in the past saying that there's absolutely no evidence for the slowdown of the AMOC based on 25 years of oleander and some 75 years analysis that a former student of mine did, Olga Sato. Unfortunately, those two studies don't really have the resolution or the time frame for looking at changes over long time scales. So this, I'm going to have to retract what I have said before in this talk. So yeah, thank you. So we'll start with just a little bit of a background, basically the work that we've been doing with the oleander and a parallel ship called the Explorer of the Seas. And that will set the stage for estimating the AMOC transport and its trend in the western North Atlantic, that is between New York, Bermuda, and Africa. And then I'll connect that to the subpolar gyre. That's much, Jamie Polka plays a big role in that part. And then I'll try to discuss a little bit the intermediate versus deep water in the North Atlantic. So with that, this button here? You have a better touch than I do. Oh, yeah, okay. So there we are. Excuse me. This is the oleander work that we've been doing since 1992 up until the end of 2018, when for various reasons we haven't been collecting data since, but we hope to restart that. And it shows substantial intervariations in the surface transport in the Gulf Stream. And because of the very high resolution of the ADCP on the oleander, we can define very accurately the instantaneous width of the stream. And that's what you're looking at here is annual averages stepped every half year, what that surface transport in the Gulf Stream itself is. But why do you have a better touch? This picture is kind of important. This is a 38 kilohertz ADCP on the Explorer of the Seas, which for a while ran along the same line as the oleander from New York to Bermuda. So we have some 57 sections reaching down to about 1,200 meters with this ADCP. And the left panel shows you the velocity, the mean velocity field in geographical coordinates for the slope. And the right panel shows you the integrals of transport in the slope sea, left of that dashed line, the Gulf Stream between the two dashed lines, and the Sargasso Sea to the right of the dashed line. So the right panel shows those three integrals, slope, stream, Sargasso, and their sums in the black line. And what's fascinating is, and this, we should have thought of this earlier, but what's fascinating is that maximum in transport, you reach a maximum at about 950, 1,000 meters or so, and then it starts to decrease again. And the reason for it is very simple, that the Gulf Stream is a highly sheared flow, but the flows to either side of the Gulf Stream are almost barotropic. And so the upper part is the Gulf Stream going north, and the lower part is everything going back south, if I put it that way. So the focus of this talk is on the very longest time scale. We're not going to look at the variability, but we're going to look at the longest time scale that we have accessible to us hydrographically. Before I move to the next slide, I should have pointed out that we could have done this with the earlier oleander data, because with the oleander, we get the surface velocity field, and we could have used that as a reference level and then integrated downwards. But now, with this hindsight, do I have to touch this first? Yeah, you have to touch. So all we're going to do, this is incredibly simple, and we could have done this a long time ago. All we're doing is looking at the potential energy difference, that is the integral of delta, specific volume anomaly, times pressure, dP, from the surface down to 1,000 meters, at the slope and at Bermuda, in two boxes defined by the polygons in the figure. So the polygons are collecting all the data within them and treating them as a homogeneous data set, as if there are no gradients with them. I think that's a reasonable thing to do. It's testable, and we have looked at it. So we looked just at how that integral chi varies over time at these two sites, and the difference between them divided by F gives us the mass transport. Pure and simple, between the slope and Bermuda. All we're doing. Do you want to touch it? Yep. Only when it translates. And these two panels, slope and Bermuda, show between 400 meters and 1,000 meters average temperature, salt density, and chi computed from the surface to 1,000 meters. For slope in Bermuda, it's rather compressed, but it goes from 1920 or so up to the present time. If we take the right panels first, that's Bermuda, you'll notice there's virtually no change. Bermuda is rock solid. But if you look at the left panel, you'll notice that there's a distinct warming in temperature, there's a distinct increase in salinity, there's a distinct decrease as a result in density, mainly due to temperature. Oh, thank you. And then finally, the chi integral, the potential energy anomaly, is increasing, which means that the difference between Bermuda, because this is less than Bermuda, it means the difference between the two is decreasing. So if we divide the difference in chi by F, we get the mass transport, the volume transport. It's about 41.8 Sverdrups, with an uncertainty specified by the uncertainty with the confidence limits in chi. We're not looking at any details, and there's a lot more that can be discussed in this figure than I have time for. So, but the problem is that the integral from the transport between the slope and Bermuda, that sums up both the AMOC going north. That's an important point, by the way. I didn't really make that. We're looking at the AMOC going north. We don't care about anything else. And the beauty is that the AMOC going north is in the Gulf Stream. It can't be anywhere else. That's the only place in the North Atlantic where water is going poleward. That simplifies our task quite a bit. But we're also getting the wind-driven circulation. So we apply the same technique from Bermuda to Africa, and we collect a lot of stations within the polygon that you can see in the left panel. And we plot them as a function of time, temperature, salt, and density and chi. And there you see a bit of an increase in temperature and salt, but you notice that the chi is almost flat. Increases ever so slightly, whether it's significant or not can be debated. That increase is comparable to Bermuda's increase, which means that the transport between Bermuda and the continent, Africa, has not been changing. And we get about 23.3 spare drips going southeast of Bermuda. We subtract that from what we got west of Bermuda, northwest of Bermuda, and we get an AMOC that's 18.5 plus minus 0.06. You shouldn't take the uncertainty too seriously because I did cheat a little bit here. And when I'm calculating the transport between the slope and Bermuda, I divide by F. So the F I use, which is different at the two ends, so I just use a single F, and I use the F where all the action is, that is at the Gulf Stream, for better or for worse. But that trend that you saw in chi in the previous figure, that is robust. And that is where all the action is taking place. So when I take this and plot up the trend over the last 80, 90 years, I'm nervous to touch this thing now. I get this figure. And this shows the black with the two red lines. That's our result. No detail whatsoever. All we're looking at is the linear fit trend to chi at slope in Bermuda in Africa. That's what we get, about 2.5 spare drips decrease over the last century or so. Now this is where the mea culpa comes in, because I always thought that these other studies were a little bit shaky, or wasn't sure how seriously I could take them. It's amazing that Chris Pykowicz's work and Caesar, I don't know her first name, their work, they fit virtually on top of each other. That is the trend. So I have moved Chris Pykowicz's work from the Florida Straits, 32, down to our figure here, just so we can compare the trends. Because almost the AMOC must be going through the Florida Straits north. And then Caesar et al., they have a very, very different approach. They only look at the anomaly, actually. They don't try to give you an absolute. I moved that up so that we could compare them. And they all have a surprisingly similar trend. But it's only over this period. Only over this period. It has no predictive value whatsoever, and it doesn't say anything about what happened before. That's an important thing that we observers have to keep in mind. Anyway, on the bottom, I also plot the work that Leon Shafik and I did of the water going into the Nordic seas. And that's a pretty robust calculation, actually done in a rather similar way with the Nordirna and hydrography between the Norwegian Sea and the Rockall Trough. There's no change. The Nordic Seas transport. And this is consistent with what people in Europe have been saying, that there's no evidence of a slowdown of the Nordic Seas overturning. So where is this slowdown coming from? Well, this is where Jamie made a very nice suggestion. I'm going to push this button and see what happens. No, you touch this and then you touch that. Wow. So here we look at the tail of the Grand Banks, and we look west and east of the tail of the Grand Banks. The picture's very easy to understand. We're looking at hydrography in those two polygons, west and east of the tail Grand Banks. And the panels below show temperature, salt, and density west and east. And you'll notice there's a phenomenal increase in temperature west of the tail of the Grand, so about 1.5 degrees, and an increase in salinity about 0.14, and a density decrease of 0.06. Whereas east of the Grand Banks, there's very little change in temperature, just slightly increased from the subpolar, slight decrease in salinity, and the same change in density. Slightly different temperature density, but it's the same trend, which is kind of interesting. If it were greatly different, there would be issues to deal with adjustments around the tail of the Grand Banks. So in some sense, it makes sense that the densities are tracking each other. But the point of this figure is that that sharp increase in temperature and salt is reflecting increased entrainment of salt water, warm salty water from the Gulf Stream at the tail of the Grand Banks. It certainly cannot come from the subpolar. That figure makes it, it's perfectly clear. I mean, there's only one place where you can find hot salty water, and that's the Gulf Stream. So why is that happening? Here we speculate, or we conjecture, that the reason is that the Gulf Stream in this region is allowed to shift farther north so that more water is getting ripped off and entrained into the recirculation, northern recirculation. And that is allowed because the stuff coming out of the Nordic, out of the subpolar gyre has weakened. It's a conjecture, that's all we can say at this point, but it seems plausible though. So I'll touch this and I'll touch it. Yeah, so to summarize, I have one more slide after this, but to summarize, we have a 2.5 SERDA decrease, manifests itself when the slope water changes. Estimating the AMOC does not depend crucially on knowing the absolute magnitude, because we're looking at the trends in the slope water sea. So that's kind of a nice result, that they're just looking at changes in the slope waters, on the slope of the slope water, that is north of the northern gyre, on the slope that is north of the northern recirculation gyre to the extent possible. And we conjecture that the decrease is due to a weaker output from the North Atlantic Intermediate Water. And now I'm going to make two more claims. One is that to the best of our knowledge, the North Atlantic Intermediate Water, that is what's coming out of the subpolar gyre, cannot seize. And that's I think it's a very straightforward statement. As you heard this morning, we know that there's an overturning taking place in the North Atlantic that reaches into the South Atlantic, but maybe not quite as deep. And the last claim is that glacial conditions, and this is really on the Wally-Broker glacial interglacial timescale. It's the glacial conditions don't depend so much on what's happening in the subpolar gyre. What's crucial is what's happening in the Nordic seas and perhaps the Arctic as well. So let me check one more slide. Can you get rid of that funny thing there? There you go. This is something I made this a long time ago. The left slide. It's the picture is from a paper by Simon Robinson in 1995, and he shows the Paleo Gulf Stream going across the North Atlantic in the middle panel. So I colorized that warm during the last glacial period, but then I take the same figure and I just colorize where we have warm water today, and that's the left panel. So you can see that the subpolar gyre, where it's really cold, where the convection is really taking place, is a pretty small area. But during the glacial times, the subpolar gyre expands enormously. The details we don't know, or at least I don't know. But the point is that we do have an active subpolar gyre at all times. It cannot shut down. And we see that from the paleo analysis. The right panel is something I fell in love with when Jake Gebbe showed it to me. It's from Laura Robinson in Science, 2005. It's showing basically the age of the deep water, the waters in the northern North Atlantic as a function of time. So going from right to left, they're going from the glacial maximum to the BA event pulling out of there, where it suddenly you suddenly start to produce deep water in the North Atlantic, and the waters turn young. Basically, they're displacing what was coming from the Southern Ocean. Then you wander into the younger Dryas, and the waters get old again. And then you come out of the younger Dryas, and you have young water again. The point about this figure is that and we see this in the rapid changes in Greenland. The point of this figure is that the Nordic seas is playing a huge role in the turn on and the turn off of the production of deep water. So the last comment I would like to make is I think it's time, we all know that we have two sources of deep water. We have the subpolar North Atlantic and we have the Nordic seas. But they're I skipped over a figure here. I missed one. It was my favorite figure. There, that one. I really would like to suggest that one of the outcomes of this group, you may disagree with me, and that's fine, but I'd really like to suggest that we start to call the waters that are coming out of the subpolar North Atlantic for North Atlantic Intermediate Water, because that's what they are. They're not deep waters. We call them deep water, but they're not really deep. The deep water is the stuff that's coming out of the subpolar, out of the Nordic seas. So I think, we know this, but I think making that distinction a little bit clearer, I think would help identify the different sources, the different mechanisms that are playing a role or contributing to the strength, the size of the AMOC. Thank you.
Any questions for Tom?
I'm happy to take questions, but I need help.
Any questions? Your question in the back.
Hi, Tom. John Toole here. I'll get closer so you can see my lips. Very nice talk. So from 2004 to 2014, at line W, we documented a slight weakening of the equatorward intermediate water flow. Trying to understand how that would translate into your New York to Bermuda transport, since I think that would be an increase in the... Right, but it just seems like the integrated transport might have actually increased.
Well,
because slope waters...
I'm looking at the trend. This study is only about the 100 years.
That's right.
Yeah. The details, there's a lot of detail, and we have started discussing about trying to delve more deeply into the hydrographic data in the slope region. Columbus Iserlohn of this institution did you guys a huge favor when he ran 15 sections from Montauk Point to Bermuda between 1937 and 1940, when they had to discontinue that on the A2, on the Atlantis. Those sections are incredibly valuable. They're high quality, the best science could do at the time. They play a big role in that picture. And then line W plays a big role as well. And of course, there are a lot of other stations. And Henry Stommel started up Station S back in 1954. And that's the reason it's so rock solid at Bermuda. I mean, we actually have better data at Bermuda than we do along our slope. So I could suggest that this institution and URI and others team up and have a program of regularly going out and doing those hydrography along the slope.
Any other questions for Tom? What happens when you're the final speaker? You can go into the discussion time a little. All right, we have a question from Chris Pykuch.
Thanks, Tom. Really nice talk. So you said it was Iserlohn that ran those initial sections. Let's take this chance, because I used a little bit of a critical adjective against what you thought my study was originally, but I'll say that appealing to Iserlohn, he was also one of the first people I know that used sea level data from the coast to try to infer changes in Gulf Stream. And if you go back to his 1940 paper, he's actually looking at sea level on the coast and infers sort of a decadal weakening in the Gulf Stream based on tide gauges from the 1920s and 1930s. So he had all the ideas.
Any other questions or comments?
Hi, I'm Lloyd Kegwin. I just want to second Tom's recommendation here. The paleo world has been looking at the North Atlantic using this as a model for approximately 35 years. And it would help bring the two communities together a little bit better. That would be the people who work with real world modern data and people that work with things we find in the mud. It would, I think it would bring the two communities a little closer together if we had kind of a standard view of what the North Atlantic looks like today. Thank you.
Is that a question? Yeah, I didn't catch the question.
I'm endorsing what you said.
All right, should we go ahead and go into discussion?
So we have about 45 minutes for discussion, and we can use the time period either to ask questions from the specific talks that weren't addressed, or to have general discussion about the task team one goals and objectives and where we stand in the future. If you guys aren't very chatty, we have some leading questions for food for thought. Oh, sure, yeah, okay.
I had a quick. Oh, okay. I'm Gökhan Danabashoğlu, so I had a question for Femke. Somewhere, yeah, right there. I guess it's mostly related to the cold blob thing. You indicated that during 2014-15 period, there was extensive convection, if I understood you correctly, and that in turn made the surface colder. So, but the convection, I would think that also bring warmer water from depth. So how do you reconcile that cold blob, in a sense, relationship with what you showed and what the other talks were this morning about the formation of the cold blob? Maybe I'm confusing things, but...
Well, the convection brings warm water up and then it cools that water down. So if you look at the whole water column, you can look at the average temperature over the upper kilometer. And if you look at the evolution of that and compare it to taking an initial temperature and just applying the surface fluxes over that 1 kilometer, you get most of the variability just by that. You have to assume some kind of constant advection because there is stratification and we don't know how that varies. But just taking that as a constant and only applying surface forcing, you get nearly most of the temperature variability over the upper kilometer.
Thank you. Yes, I did. Sorry, yeah. Danabashoğlu. It's so easy, nobody pronounces it. That's the problem.
So maybe, do we have anything from the folks online?
Yes, Gerard, do you have a question? Would you like to unmute?
Yeah, so I have a question for Tom, actually. I was hoping to catch him before I went. I just realized that it's gone very dark on this side of the Atlantic, but I'm glad I stayed with it for the last talk. The question was for Tom. It was actually about where he thinks the data can go in terms of the hydrography. Does he think that he'd be able to resolve decadal trends that might be in the hydrographic data? I guess some of the kind of issues around, say, Lev-Caesar's index and some of the I suppose the climate models in particular have shown quite distinctly different trends through the 60s. So I was just wondering if there's kind of potential to address that issue with those data.
That was a question for you, Tom.
Yes, well, you and I have just started discussing that, and we probably can. Bermuda is rock solid. There is some interesting signals in the Bermuda record around 1970 when it dipped. The period around 1965 to early 70s is extremely interesting. But apart from that, the 32 line Africa to Bermuda is rock solid. All the action is at the slope. And so we are starting to think about how to dig in deeper into the slope data, including XBTs, because there are a lot of XBTs, which we can sort of remap into hydrography and thus zoom in. What it will tell us, I don't know. Whether it connects to, actually there was one point that I could have made in the slope hydrography in the 1960s, it got much fresher and colder for a while. And that's, we think, is because during that low NAO period, the Gulf Stream shifted farther south and allowed much more North Atlantic water to get into the slope sea. So what's that? The point of that is that, yes, we can look at shorter timescales. I think so.
Brilliant.
And when
That's
you
great.
say rock solid, you mean no interannual variability or no trend? No trend.
We're treating this as quasi-steady state signals as when there's no dynamics in it. I don't.
Okay, other questions here in the room or on the chat? Otherwise, I'll ask you questions. Okay, so do you all think, beginning of the AMOC studies, I didn't even need these. Okay, so can we design a practical system for long-term monitoring of the AMOC? That's a great question, practical, but not so cheap that it's missing the action. Is somebody almost raising their hand back there now? Yes.
Hello. Hi, Dan Amran from NCAR. I guess we've heard mentioned a couple of times the possibility of an Argo plus altimeter option for monitoring, and it'd be great to hear a little bit more about what's entailed there and what some of the pros and cons are, the current state of that.
Okay, before we go there, is that in response to this? Yes, okay. Yes, okay, so Renellys wanted to reply to that?
Hi, can you hear me?
We can hear you, yep.
I don't know
And
what
we
I
can see you.
I don't know what I just did with my background, but it's funny. I guess I was thinking about the bottom pressure conversation. You know, we talked about the instruments that we use have pressure drift, and until we can fully solve that, which I'm glad that there's technology that will help us do that, we could do, you know, it's not less expensive, have tandem deployments in staggered years of these bottom pressure sensors so that we can do a better job of getting rid of the drift. And I think we all rely on satellite winds or some kind of reanalysis product to give us an estimate of the Ekman component. So I think there's a really low-hanging fruit there to ensure that we can continue to have good quality winds that we can all use for the Ekman component.
So that sounds like a combination of some moorings going on, but then satellites and Argo.
Yeah, I mean, I think so, yes.
Oh, go ahead, Renellys.
Yeah, I think having more arrays that maybe become more scaled back over time, but we need to have the, you know, a long enough record to be able to say what a logical scaled back would be, and a combination of that with in situ measurements and satellite altimetry and scatterometry, or whatever wind satellite technology is best.
Mike, did you want to add?
Yeah, so I seem to remember reading papers, I couldn't say exactly where and when, that ocean models, either reanalysis or forward models that are forced with reanalysis products from the atmosphere, do a pretty good job of reproducing measured MOC transports, mean and variability. So I know the models diverge projecting forward in time, coupled models, right? But if we're just talking about reproducing what's there, is there a way to supplement some minimal level of observations with either assimilating or forward models? Maybe Gökhan or Steve, you guys have done some of this kind of work.
Actually, could I just like throw another question into the mixed answer here? So I just want to build on Dan's question, which is in addition to Argo and altimetry, things like tide gauges and GRACE. So yeah, I really think we should take stock of what the global ocean observing system is and what information content about North Atlantic circulation lies in these different observing platforms. And the others I would actually kind of generalize from Mike's question, you know, using ocean models to say crudely interpolate between where we have data. I think that brings up the bigger point of understanding the spatiotemporal covariance of ocean variability. Maybe that's informed by a model, but you know, we should, I think making that question an explicit science question could be really helpful, sort of blowing it up to that. Certainly models inform that in our physics base, but there are other ways as well. I'll let Steve answer all that.
I was just going to make the point that we're just starting to look at how eddy resolving ocean models forced with reanalysis can reproduce observed variability, and there's you know, the problem gets a lot harder when you have intrinsic ocean noise in your ocean model. And so I have a poster on that tomorrow that kind of shows the signal to noise that you get in one of these forced ocean simulations that has eddies. We still get significant signal, but it's not as much as in the coarse resolution.
Be a little bit controversial statement so that it'll spark maybe more discussion. From the modeling world, I think we can more or less say that AMOC has been declining over the last maybe 2 decades. It might be small, but I don't think that we can say the same statement from available observational estimates at this point for the same time period. So as I showed this morning, and I don't know how the new sort of modified MOVE array will show, but while RAPID is showing a decline, MOVE is showing an increase, and perhaps SAMBA and OSNAP at this point is too short to say anything on longer time scales. So that's another thing that we can probably bring models and observations together. And I know the difficulties associated with different observational programs, and they do whatever best for them. But at some point, to reconcile some of these differences, I think maybe details of methodology make a difference. So I mean, I know each observational program thinks that, well, that'll be too controversial probably, but I mean, everybody thinks that their method is the best one or maybe best fit for that particular array. But I think reconciling those, and that's what we are working on the AMOC metrics project, and we are collaborating with observational folks. But I think at the end of the day, if somebody asks me what the observations are saying, what AMOC is doing over the last 20 years, I don't know the answer. And from the models, I can say that it's declining, but not from observations.
Renellys, did you have something to say? I see your camera on.
Well, yeah. I just wanted to, I think along with the lines of what Gökhan was saying is that some of these arrays are not intentionally constructed to measure AMOC. It's a benefit of boundary arrays. So we're stitching together boundary arrays and getting an added value out of them, and they're intentionally deployed to measure things of interest to the countries that are measuring them. So I think that's one of the inherent problems that we have in coming up with this sort of like fit for purpose AMOC observing system.
I have a question that kind of ties into what Tom was saying about the importance of the Nordic seas, and also what Wilbert was saying earlier about connecting to the Arctic Ocean. There's a number of moorings array in the north also that don't show up in some of the maps that we've seen today. For example, there's an array in Franz Strait. There's one near the Faroe Islands. Denmark flow water has been measured for quite a while. If the Nordic Seas and Arctic is so important, should we do a better job in including these observations in the story as well and making use of them?
So, Matthias? Matthias?
Yes, hi. Can you hear me?
We can hear you, yep.
Okay, good, yeah. Okay. Yeah, to Gökhan, I share the concern that there is no coherent consensus among the different observing systems, but I do think we are making progress. I will include some of that in my talk later this week, but I think we now have versions of transport time series at MOVE and at the 26 North array that are more consistent on decadal trends than what we've had in the past. So maybe we're making progress there. So and what I'm seeing, I can say that already, is we're seeing decadal oscillation. So not a decline or increase, but it's going up in one period and down in the other. So more to come later. Thank you.
I'll read maybe Renellys' question here. What is the best way to measure time variability of AMOC between 10 South and 10 North? is it important to measure it?
Yeah, I was just throwing it out to be provocative. If we're talking about unifying the way moving to doing things in a more unified way, that's kind of hard to do it in the region where you can't divide by F.
This is a little bit of a takeoff on what I just spoke about. We're looking at the Gulf Stream, the AMOC going north, where it's extremely well defined. And likewise, Chris did so in a manner of speaking in the Florida Straits. Getting back to what Gökhan was saying, could a case be made that we should be looking at what's going north for coherence? Because what's going south, it's got so many different pathways, depths, recirculations, and so forth. I mean, it's not a pipe exactly, it's a very leaky pipe, but it at least is in some sense well defined what's going north. Would that help to look at meridional coherence?
One of the other related questions or sets of questions is what needs to be monitored? Heat, fresh water, or carbon? Or are we satisfied just with AMOC strength? That doesn't sound like a very sunsetty statement. For those of you online, Gökhan just suggested all of the above and maybe more.
Hey, oh, sorry, I'm just going to follow up on that in a way, or it's a slightly different question, but I guess I don't know the answer. My question is, do we have a technology to actually measure transports that are, deployable at scale, as compared to, putting moorings and then providing a framework with like conservation of volume to get to transports? Do we have technologies that are feasible to deploy at scale and actually measure transport?
These on commercial ships?
I'll put another question out there. Maybe Dan or somebody else can, or maybe Gael, I guess. For data assimilation purposes, usually what we also hear, in addition to a bunch of other challenges, is that having, as I said this morning, deep observations would be very helpful to constrain AMOC. But if we also look at both the eastern and western side of the Atlantic and the missing sort of data areas near the coastal lines or over the continental shelves, they seem to be missing as well. And that might be important to set the east-west pressure gradient for the north-south flow. So in your opinion, for data assimilation purposes or reanalysis purposes that can be used for initialization of Earth system predictions, what are the crucial data sets that are missing in the North Atlantic? I'm not sure I have the answer, but I might try that we are not missing anything. Is it possible that with the satellite measurements that we have for bottom pressure, for sea level, right, with all of the hydrography that we have, that's key to making all of the transport estimates in the ocean interior for the open ocean, and with scatterometry and with some things like the Florida Strait transport, maybe we have enough constraints. It's unclear to me that something like global deep cargo, for example, is crucial to that goal. It's not obvious to me at all. Near the boundaries, I think the more measurements you have, the better. But I'm just a guess.
Yeah, just a quick response to Uwe's end. I'm not sure we have enough observations in the really deep ocean, like below 2,000 meters or so, because in our analyses at MOVE, we find that long-term changes in the transport depend very sensitively on the small, gradual changes in salinity down there. And the same salinity trends are found at the other latitudes. Rapid sees them, and I think in the South Atlantic you'll see them too. So in our geostrophic calculations, many of the long-term changes come from these very deep salinity trends. And each time we try to look in models to see whether we can simulate our observations or look at the processes in models, we found that the models do not correctly represent these deep salinity changes, which somehow means the models are not constrained enough down there, especially with regard to salinity. And in our analysis, it looks like salinity is really crucial for getting the pressure gradients right. So I think it would really help to constrain the models better for the deep salinities.
I guess I would add, Gökhan, your question poses a hypothesis, and I think it's a hypothesis that could be tested by maybe extending some of these OSSEs and other experiments. In the context of a perfect model world, you could ask, at what point are we able to reconstruct all of the features of the overturning circulation that we're interested in? And then think about what features of an observing system are really crucial there. But your question was also about predictability, and I think that kind of extends, the scope of data assimilation, because it's not just necessarily about giving a best guess of a state at a particular time, but a range of uncertainties that represents, our lack of knowledge about the ocean. And so I think that's one of the places, too, where the deep ocean comes into play, and also the role of data assimilation in trying to understand where models subsequently go wrong once you let them free in that sort of forecast mode.
We have votes for deep ocean observations, salinities, deep salinities. One second, Tom.
Yeah, this is Gail again. And just to add something to my earlier answer, I think one thing that we need is some kind of measurements of water mass transformation in the ocean interior. So we're going to mix things essentially. So those terms, right, that are also hard to observe. I think that's one thing I would like to have more constraints on, diabatic processes in the ocean interior.
I didn't hear the last conversations very well, so this may be a non sequitur, but one thing that has fascinated me is that back in the 1960s, when we had a strong low NAO period, we had rather cold weather here in New England, by the way. We had a lot of water from the Labrador Sea flooding into the Slope Sea. We know this from the stuff that I showed you now, the hydrographic record. So the Gulf Stream was pushed to the south, and much more of the Labrador Sea water was getting into the Slope Sea and to the west during that low NAO period. When you have a high NAO period, we starve that flow to the south and to the west, and the Gulf Stream shifts north. And we have deep convection in the Labrador Sea and the Erminger Sea. And those waters, in some sense, tend to spread to the east instead. So you have, assuming you have about the same amount of water coming around Greenland feeding the Labrador Sea and the Erminger Sea, assuming it's roughly the same, regardless of NAO. When you have a low NAO, you're shipping water south. When you have a high NAO, you're shipping water deeper. Well, I don't know if it's deeper, but you're shipping convected water off to the east, more to the east. Which is high NAO? I'm sorry, which is a fast AMOC and which is a slow AMOC, and why? I don't understand that. Maybe everybody else does, but I don't.
You have to.
When I talk about AMOC transport variabilities, I mean, it seems to focus mostly on the production. But I mean, I'm just trying to reflect the lunch table discussion here. It's really not only the production, but it's also the supply chain, the transport. We're talking, so you can have plenty of deep water being formed or in the inventory, but it's the mechanism that regulate the transport change. For instance, I mean, based on Nelson and Henry Stomo's work about Gulf Stream extension as a potential vorticity barrier for regulating the intermediate, the upper North Atlantic deep water export. And also something like what Mike Spohr and Firma did about the balcony instabilities about boundary current. A lot of those things can change without changing the production itself.
Very modern problem, supply chain issues. Online, Renellys.
Oh, yeah, just following up on the point about the models and what could be useful to assimilate into them. I was just thinking back to the work that Shen-Fu Dong did a few years ago, looking at model seasonal cycle in the South Atlantic of the MOC. And it turned out that the model seasonal cycle was much weaker than observed. And, so you could stop there, but the reason for it was because the models were too baroclinic. And the models had too much vertical stratification. And so the vertical structure of not just of the velocity and the MOC was not right, but there was a density reason on the boundaries, the two boundaries for that disagreement. So I think there's still a value to more observations being assimilated to improve the vertical structure of temperature and salinity and density in the upper 1,000 meters and beyond as we start thinking about deep Argo.
Hi, this is Yao from Georgia Tech again. So I have a comment. I think we have talked about today a lot about the area observation, but I think follow up from Jira's comment that we should have a better use of those hydrographic data. And I believe at the moment there have been several studies based on hydrographic reconstruction data and showed that in the past probably 30 years that AMOC was relatively stable, or at least on decadal timescales, the AMOC variability is relatively small. So, for example, Worthington's work, or one of the work of myself, and also I think Veronica's work, who is also here. So these work have used basically hydrographic data, and I think prior to the area observations, there are plenty of hydrographic section data from the beginning of the 1990s, and I think we should have a better use of those data. Thank you.
Gerard?
Yeah, I would kind of agree with that point, and I'd probably kind of say that that's kind of very much of kind of what I'd see kind of a vanguard of things as well. Going back to Gokken's question about whether the observations agreed or disagreed in the last 20 years, I would say they definitely agree, actually. I know exactly what they did. And I think I would have said that MOVE was maybe an exception to that right up until your talk this morning, Gokken. And I think that's what Matthias was talking about as well. As far as I could read that plot was that there's a weakening of the deep western boundary current until about 2010 and a strengthening thereafter. And I think that's seen in all the reconstructions and the direct observations. When you go back further in time, you are reliant on hydrography, and that's when things get a lot more uncertain, I would say.
Thanks very much. So Chris Paikush from WHOI. Yeah, just a comment on the past three questions about hydrography. Would fully agree. Yeah, we need to sort of extract all the information content from these data, but I think we need to think really hard about how we use the data. You know, how are we assimilating these? You know, for example, that Gael has worked on is using physically consistent state estimation to bring these into a system where you're assimilating the model into a known physics. But something that worries, I think we all remember Bryden et al. 2005. I think we have to be very aware of the possibility of aliasing if we were to just take half a dozen hydrographic sections over a 30-year period. There's a very real possibility of aliasing. So I think we need to think very carefully about how we make estimation from those absolutely incredibly valuable data. I think we need to treat them with the respect they deserve, so to speak.
So I think we are coming, oh no, I guess we still have a little bit more. All right, so while we're thinking of our last couple of comments, we have 7 more minutes. Gokhan at the beginning, I think, did a really nice job of saying what a big family the AMOC family is. It's not just PIs, but it's postdocs and students too. A lot of folks who have put a lot, I guess, built their careers on AMOC research, and it's a really big tent. And I just wanted to, since this is Task Team 1, I just wanted to make sure that that family includes the people who go to sea and the people who process the data. Like all of these time series, we look at these little lines, these squiggly lines, but there's so much that goes into it. So yeah, hooray for observations. And if you look at pictures of people who went to sea 10 years ago or 15 years ago, they look like babies. Do you know what those are, Gokhan? For real? Have you come to see? All right, so this is the cups, the styrofoam cups that you put on your 5,000-meter casts, and they get crushed by pressure. And it's not on here, but my actual favorite picture of going to sea is of John Toole and Bill Smethy decorating cups on one of the last Line W cruises. So yeah, right. So both also the U.S. academic research fleet are foreign collaborators with their vessels, and then of course the commercial vessels as well. Like going to sea, you need all kinds. Okay, that was my little soapbox. 6 more minutes for thoughts about AMOC. And there, we have a third motivating question. Kathy doesn't like this one, thinks it's boring. But it is, okay, related to design, how can we get a better this is up your alley, Chris. How can we get a better quantification or understanding of the uncertainties associated with our observational AMOC estimates? And I guess part of it is maybe what was advocated this morning, like let your secrets out, like report your compensation velocity or transports and your leveling methodology. Your confession session. But are there other things we can think about so that we are reporting honest uncertainties?
Back to the comment earlier about using models and efficient use of OSSEs to tell us how to design the observing system. So my question is, you said that you would use the OSSEs to investigate certain features of the AMOC. Is what parts of the AMOC do we need to be measuring? Like, what's the larger question of what do we need to know? Because we need to know how much deep water is being formed, but we also need to know how it's advected. We have a really contemporary problem of understanding where carbon's going. And so I guess I would say for those of you that are working on that would work on this problem, what would you look at first?
Now I'm on. If anyone has any answers to that question, that's fine. I don't. I have an announcement. So the paleo, if you self-identify in the paleo community, please come for a discussion at lunch. We're going to just talk about next steps and strategize a little bit. And we'll do this in the Bigelow building, a couple blocks down. So at lunchtime, grab your lunch and then meet out front, and we'll walk over.
You'll have a virtual component to it, right?
We will have a virtual component. If you registered interest in Paleo AMOC when you registered for this meeting, I have spammed you with a Zoom link. So if you didn't get that, I'm Hallie Kilborn, and find my email and ping me. Thanks.
Should we hijack this for another announcement? Shuttles?
Yeah, so I'm going to drive the shuttle back to the Inn on the Square and the Holiday Inn after our little reception thing here. So it'll be at 7:30. And I had 2 runs this morning. Wasn't overwhelming demand. So tomorrow morning is just going to be one drive. I'll be at the Holiday Inn at 7:20 and Inn on the Square at 7:30. If you miss it, you're on your own.
I can also take people in the morning from the Inn at Holiday Inn. No, I don't want to be on the shuttle.
So before talking about transportation, I had maybe an answer for Magdalena. So, so one of the things so I was on the Phenomena Observation and Synthesis panel of US CLIVAR for 5 years. And so one of the things that we talked about a lot is the availability of the data from all these observational arrays. So I think we're doing collectively a much better job that we used to do in terms of not only making your time series viable, but making available your methods, right? So we should do better. So if we want to understand, the uncertainties, we need to understand the methods that are being applied to actually derive all those time series. So I understand that, we work very hard to get the funding. We get those millions of dollars to get those observations, and we're a bit protective. But in terms of open science and open data, I think it is very much time to maybe change the way we work. And so as an example, at Rapid 26 North, it would be amazing if we actually had an open workflow allowing us to understand how we go from the mooring profile, the individual CTDs, to the calculation of the transport. So we can work on that. And I think everybody should work on that. One of the recommendations also from US CLIVAR for a very long time is to have a centralized, portal or database where we could be, centralizing all the time series and all the methods that are being applied, right? And I know everybody published papers about the methods, but you need to have, code available as well so that we can, not replicate, but we can try to understand better how things are derived and maybe improve it as time goes on. Femke noticed that, there's a lot of other data sets that are available. So how do we solve that problem of making those data sets available or usable for everybody else, right? So if you have suggestions, please let us know.
A lot of these data sets are available through OceanSites, for example, which is a storage for mooring data, but it's hard to assess for reanalysis, for example. They don't like mooring data as much as Argo data. But sharing code is definitely more important. I agree there.
So one of the things that people discuss nowadays is that available is one thing, but accessibility is a different thing, right? So let's go from available to accessible so that it could be shared more widely. And we can understand the uncertainties by looking at uncertainties that come from the different methods that are being applied to the data set, as well as the models and everything.
I have a follow-up. So I'm at the moment responsible for processing the OSNAP data. So for producing the OSNAP time series. So basically, I could briefly introduce how I did that. So basically, the OSNAP project is really a collaboration of international institutes. So we have in the laboratory the German 53° north area, and in the eastern boundary of the laboratory we have the Bob Picard's West Korean current area, and also in the Erminger Sea we have the deep western boundary current area and the Erminger current area. And on the Iceland Basin side, we have the Iceland Basin moorings and also in the Rockall Trough, and there's the Sams Rockall Trough moorings. So basically, I gather all the processed mooring from each of the groups and gather them together and put them by calculating first. If we have direct velocity measurements, I use those direct velocity measurements. But if, say, between two moorings, there's an open space, we use geostrophic calculation. So the OSNAP calculation code in total is more than 8,000 lines in MATLAB. So in words of saying open that code would require, a substantial time for anybody to really understand what is going on. So I think it's really difficult to say that that code can be available. The code is, of course, can be available to everybody, but to let everybody understand that code is really a hard work. I think we need to find a better way to,
So, yeah, I'm not asking you to do more work. What I'm asking you is to think differently and, try to attract more funding to do it differently. Do you know what I mean? So you can actually, there are some, research programs that are going to fund you to develop like cyber infrastructure, code development, software. And so we have to think differently in terms of funding people to actually do that. Turn your code into, an open language and put it available for everybody to, help you.
Thank you.
Yeah, Gaël Forget, and I'm going to take my hat off MIT GCM now. In the modeling communities, we've been doing this effort for decades, and it is some effort, right? It requires spending time, creating ways to replicate your results, most importantly, possibly good documentation, and all of that does take effort, but it's crucial to the value of, the science we produce, that it can be understood. What you're telling me that the code that generates OSNAP, you're the only person in the world that understands those 8,000 lines of code, that worries me.
Maybe you shouldn't take the shuttle tomorrow morning, Mike. So we're a little after 6. We're supposed to end at 6, right? So in the interest of keeping on schedule and socializing sooner rather than later, over beer? Yeah. We'll wrap it up and save the rest of the discussion for either one of the other discussion sessions or for Thursday. Thanks, everybody, for participating.
We'll meet here tomorrow, same time. For the virtual folks, the same link.